Welcome to this video on Euler's method, a way of seeing what a function looks like given only its derivative and a starting point. So before we get started, try this quick warm up here, find the derivative of this function, and then see if you can tell how much this function's y value will change when x changes by 0.05. You can pause the video and work the problem out. And now we're back. Let's see what the solution is here. The derivative of y equals 4x minus 8 is, of course, dy dx equal to 4. So that means this line has a slope of 4. This is, of course, a linear equation. And to find how much the y value would change if we only go over by 0.05, we could take dy dx, multiply both sides times dx, or a very small change in x, and we'll get the change in y is equal to 4 times the change in x, or 4 times 0.05. And 4 times 0.05 is 0.2. So when we go over a small amount, we go up just a little bit. If we were to do this 20 times, we would wind up going over 1 and up 4. And of course, that's the nature of a linear equation. As we go over, we go up the same amount every time. But now let's try a second warm up. See if you can find a formula for the differential dy for the function y equals 3x squared minus 5x, and use that differential to estimate the change in y when x changes by 0.05. So you can pause the video and try this out yourself. So let's get back to the problem here. You probably devised that dy dx for this function is 6x minus 5. Therefore, dy would equal 6x minus 5 times dx. Now, there is a bit of a problem with this next question, because this is a quadratic, it's a parabola. If I change x by 0.05, I'm going to have a different change in y depending on where on the parabola I am. If I'm close to the vertex of the parabola, changing by 0.05 is not going to cause the y value to change very much. But if I go over several steps away from the vertex, changing by 0.05, I'll be on a much steeper part of the graph and the y will change much more. If I go very far away from the vertex and change x by 0.05, I'll be at a very steep place on the parabola, and that y value will change even more. So I need to add a little bit more to this question, be a little more specific. Let's say we want to know the change in y when x changes by 0.05 with a starting value of x equals 2. So now that I'm a little more specific, see if you can calculate that. Well, here's how we'd go about this. We take the formula above, dy equals 6x minus 5 times dx. We plug in an x value of 2 for x and plug in 0.05 for dx. And calculating, that's 12 minus 5, so 7 times 0.05, and that comes out to 0.35. So this is approximately how much the y value will change if we change x by 0.05 and have a starting value of 2. Just to kind of check to see that this matches up with reality here. Over here, I've done some calculations. I went back to the original equation and plugged in 2, and the original equation and plugged in 2.05. And you can see we changed from a y value of 2 to a y value of 2.3575. Now, this method of finding a change in y does not give us the exact change in y. It gives us an approximate change in y. So really the y value changed by 0.3575, but our approximation was 0.35. What we're aiming at is we're going to try to find a function given a derivative. So here's a few problems that we've learned to do in the past. We try to find the general antiderivative for a function. And let's see how this would work out. The general antiderivative for g of x, maybe we call it capital G of x. And we have to do the antiderivative term by term. X cubed, antiderivative would be x to the fourth over 4. 2x's antiderivative is plus x squared. And negative square root of x, well, let's see, that's like a negative x to the 1 over 2. So add 1 to the power, divide by the new power. That would be minus 2/3 x to the 3 halves. So I added 1 to the power, divided by the new power. And this is just a general antiderivative. It could have any constant at all at the end of this. Now let's go to this next problem. They give us a second derivative and some additional information, and they ask us to work our way back up to the function, f of x. Well, let's see if we can do that. From the second derivative, I could say that f prime of x looks like this, x cubed over 3, negative 4x to the 1/2. And you can check that by taking the derivative of this, see if you do get negative 2 over square root of x. And then the antiderivative of 1 would be x. And again, we have a plus c, but this time we have enough information to find that constant. So by plugging in 1 for x and negative 3 for f prime, we could get the value for c. It's negative 3 equals 1/3 minus 4 square root of 1 plus 1 plus c. So add 4 and subtract 1. 0 equals 1/3 plus c, and c equal to negative 1/3. So our real f prime of x is x cubed over 3 minus 4x to the 1/2 plus x minus 1/3. And now to get to capital F of x, we could do the same thing. Take the antiderivative, see, add 1 to the power, divide by the new power, that's x to the 4th over 12. Add 1 to the power, divide by the new power, that would be minus 8/3 x to the 3 halves. And antiderivative of x is x squared over 2. Antiderivative of negative 1/3 is negative 1/3 x. And then originally we have a plus c here for a constant, but with the information 1 and 2, we can now find that constant. So as you can see with the work over here on the left, we get a c value of 53 over 12 when we plug in 1 for x and 2 for f of x. So our final answer there is that f of x is equal to x to the 4th over 12 minus 8/3 x to the 3 halves plus x squared over 2 minus x over 3 plus 53 over 12. Now, finding these antiderivatives is not trivial. That's a little bit of work, especially when you have fractional exponents, negative exponents, when you actually have to find that c value. These things can get pretty complicated. Now, as we get down to this last question here, we have a derivative, dy dx equals 2x plus y. We do have a function value at 0. The value is 1. And we're wondering, what function does this derivative come from? Well, this is a difficult question to answer. Finding the antiderivative of 2x plus y is not like any antiderivative we've ever found before. We've always done antiderivatives of a single variable, not of 2 variables. So what function does this thing come from? Well, Euler's method is a method to help us solve these problems as they get more and more difficult to figure out the antiderivative of. So here's a picture of Leonhard Euler. You pronounce his name Euler, not Euler. Leonhard Euler was a very famous mathematician, lived in the 18th century, and he made a lot of very important contributions to mathematics. In fact, we have him to thank for the following notations: function notation, f of x, calling the base of the natural log e. I don't know, maybe he named it after himself there, Euler. Using the symbol pi for the ratio of circumference to diameter on a circle. The I notation for the square root of -1. So Euler did a lot of study on complex numbers. And summation notation, this sigma notation for a sum. One of the things he talked about a lot was delta y as a finite change in y and delta x as a finite change in x. Leonhard Euler came up with a method for approximating what a function would look like if we only know its derivative and a starting point. When we'll use this approximation method is for differential equations that cannot be solved. So we're going to start by practicing with an easy one that we can solve so that we can check our solution and see if it matches up with reality here. So we're going to start with dy dx equals 2x and an initial value y sub 0 equals 1, or a y value of 1 when x equals 0. Now, 2x is not a very difficult formula to find the antiderivative of, but let's follow Euler's method just so we can see how this whole thing works. Here are the steps that we're going to follow. The concept is we're going to start at a given point, calculate a differential to estimate the change in y. Then we'll go up dy and over dx and plot a new point. This is similar to how we've graphed linear equations in the past. We have a starting point, sometimes it's the y-intercept, and then the derivative or the slope tells us how far up to go and how far over to go. Well, this time, every step we take, the slope is going to be a little bit different. So we'll go up a different amount and, well, usually over the same amount. And we'll repeat this as often as desired. So you'll see we'll calculate, we'll be given dy dx, and we'll be given a certain point to start at, xy. We're going to solve for dy, use current values to find dy, a numerical value for dy. We'll go up a little bit and over a little bit to a new point, and then we'll repeat the process all over again. Use these new x and y values to find a new dy, go up and over, and use the new values to find a new dy. And we'll repeat as often as we need to. So as I said, we're starting with dy dx equals 2x. Well, dy dx equals 2x could also be written in the form of a differential. dy equals 2x dx. I'm going to use the initial starting point, 0 and 1, and a dx of 0.5 to calculate dy. So I'll plug in 0 for x and 0.5 for dx. That's going to get me from an initial point to a new point. The change in y is 2 times 0 times 0.5, or 0. So my new y value is going to be 1 plus 0. So I go up 0 and over 0.5. I get a new point, and I can plot that on my graph. Now I'm going to use the new x and y value, 0.5 for x, 1 for y, and 0.5 for dx, and calculate a new dy value. 2 times 0.5 times 0.5 is 0.5. And so I'll add that to my previous y value to get 1.5. So I'm going to plot now the point 1, 1.5. That would be approximately right here. And I'm going to use the new values 1 and 1.5 to do this calculation again. dy equals 2 times 1 times dx, again, is 0.5. And this comes out to 1. A dy of 1 means I go up 1 from my previous y value. My new y value is going to be 2.5. Now I'll use these values to calculate dy again. Use 1.5 for x, 2.5 for y, and 0.5 for dx. 2 times 1.5 times 0.5 equals 1.5. Add 1.5 to the previous y value, and we get a y value of 4. We could go further, but I think that's far enough to now see a starting shape for this function. This is an approximation of the function that has derivative 2x and has an initial value of 0, 1. Now let's compare that to the exact solution. We know that the antiderivative of 2x is x squared. That is x squared plus c. And with the initial values 0 and 1, we can plug those values in to find the constant value. The constant is 1. So my function is y equals x squared plus 1. Here's what the parabola x squared plus 1 looks like. And you can see that this red approximation graph follows it fairly closely. To get a more accurate approximation, what we would need to do is use a smaller dx. So instead of jumping by 0.5 each time, maybe we could jump by 0.2 each time. Or maybe we could jump by 0.1 each time. Of course, the smaller we make our steps, the longer it's going to take to get to whatever x value we desire. So if I use steps of 0.2 and try to get to 2, it's going to take me 10 steps to get there. If I use steps of 0.1, it's going to take me 20 steps to get from 0 to 2. That'll be a much more accurate approximation of this graph, but it takes many more steps to go. But the fact is, Euler's method is only an approximation, and it will always get less accurate the farther away we move from that initial value. So by making those steps smaller, I can stay close to this curve for a while, but eventually, no matter how small I make those steps, it will eventually start to break away from the actual curve. Now, I want to finish this off with a second example using kind of an alternate version of Euler's method. Here's what we're going to do in this method. We're going to be given dy dx and a starting x value and y value. We're going to plug in that current x and y value to find dy dx. Then here's where it's going to be a little bit different. Use the point slope form of a tangent line to calculate the next y value. So let me show you what I mean. When I do Euler's method, I like to keep track of things in a table. We have dy dx equals 2x plus y with a starting value of 0, 1. I'm going to take steps delta x of 0.1, and I want to find the y value when x equals 1.4. So my current x is 0, my current y value is 1. Using those two values, I can calculate dy dx, 2 times 0 plus 1. So dy dx equals 1. Now we go over to this familiar form of an equation of a line. Same thing we've used when we've done linearization or equation of a tangent line. And we're going to say y equals, well, dy dx we just calculated, 1. And then where we usually see x minus x1, we're going to take the next x value and subtract the current x value, and basically that's going to be our step. So our next x value is going to be 0.1. 0.1 minus 0 is 0.1. And then we're going to add the current y value, which was a 1. Y equals 1 times 0.1 plus 1. And so that comes out to 1.1. That's our new y value. Now we're going to repeat this process. Using this as our x value and this as our y value, find dy dx. 2 times 0.1 plus 1.1. And that gets us to 1.3. Put this into our point slope form. 1.3 is the slope. Our delta x, x minus x1 is still going to be 0.1 because in our next step, we're just going to move by 0.1 again. And our y value is 1.1. If we add these up, I think I can still do this in my head. I believe we get 1.23. From here out, I'm going to start using a calculator to do these calculations. So let's calculate the dy dx when we use an x value of 0.2 and a y value of 1.23. So on a calculator, I see that that equals 1.63. And now again, using this point slope form, I'll use 1.63 for my slope, 0.1 for my change in x, and 1.23 as my previous y value. So I have an x value of 0.3, y value of 1.393, and I'm going to use these two values to calculate dy dx again. Notice I'm still using the formula for dy dx, 2 times x plus y, 2 times 0.3 times 1.393, and the calculator this time gives me 1.993. Put that in my point slope form, that is the slope, 1.993 times the change in x. Remember, the change in x is always the same amount. I'm always moving over the same steps. So 0.1 for change in x and add the y value 1.393. When I put those numbers in my calculator, I get 1.5923. 1.593. And so the y value at 0.4 is 1.5923. And in only 10 more steps, we'll be at x equals 1.4. Whoa, did I say y at x equals 1.4? I think I meant y when x equals 0.4. Yeah, to take 10 steps would be kind of ridiculous. This process is actually very easily automated, and you can put it onto a computer. But if you're doing this by hand, you can expect maybe to have to do 2 or 3 steps to get to your final y value. So there's Eulers' method, kind of 2 different approaches. I definitely recommend that you keep track of your work in some kind of a table of values. I'll be looking for a table of values like this when I test you over Eulers' method. So go ahead and try the assignment on Eulers' method, and I'll see you next time.